As the 20th century dawned, all fabrics were natural. But chemists had a dream: to develop and manufacture new materials with exceptional properties. Two Swiss-born brothers, Camille and Henry Dreyfus, pursued that dream while working on their PhDs in chemistry at the University of Basel. They started with cellulose, the tough, insoluble fiber found in trees. Henry Walter, Foundation president and member of the Dreyfus family, explains how they began.
The first innovation was trying to replace cellulose nitrate and produce something that wasn't as flammable.
The answer was cellulose acetate. But before they could develop it into a fiber, World War I broke out. The Dreyfus brothers provided the Allies with non-flammable coatings for airplanes. After the war,
they did something like 20,000 experiments,
resulting in a fiber that could be woven and dyed. Their company, Celanese, became a pillar of the synthetic textile industry. By mid-century, the company grew to be one of the world's largest. Their dyeable, award-winning silk-like fiber became a fashion staple.
Cellulose is very difficult to use. You have to act on it very vigorously.
The Dreyfus brothers broke it down with acetic anhydride. Acetate reacts with hydroxyl groups on cellulose sugars, so that
cellulose acetate now becomes soluble in a whole range of solvents, making it a lot easier to shape and form.
One important use was movie film,
which solved a huge problem for the movie industry because earlier versions of movie film would burst into flames.
Cellulose acetate is still in use today in product design and in 3D printers. Henry died in 1944. In his memory, Camille started the Dreyfus Foundation in 1946, explaining why in a letter.
We shared together the sweat and tears of labor and disappointment and the joys of achievement. Henry was to me my loyal, true, and dearly beloved brother.
In 1949, the name of the foundation was changed to the Camille and Henry Dreyfus Foundation to link both brothers forever in promoting chemistry, the field they loved so well. Camille Dreyfus knew what he wanted the foundation to do.
He said the foundation's goals were to advance the science of chemistry, chemical engineering, and related sciences as a means of improving human circumstances and relations. The foundation programs are designed to identify scientists at important stages of their careers.
The important thing for the Dreyfus Foundation is not to see the future, but rather to enable the future to unfold.
One program is the Environmental Postdoctoral Fellowship.
That was in many ways a gateway to allow PhDs in physical chemistry, for example, to move directly into an arena that collided basic science with public policy change.
The Dreyfus Prize recognizes major chemistry achievements with a $250,000 award.
One characteristic of the Dreyfus Prize is that it's an area which transcends subdisciplinary boundaries.
The inaugural prize was awarded to Harvard materials chemist George Whitesides in 2009.
I'd say George Whitesides is one of the best in the world in taking achievements from one area of chemistry and applying them in another area.
The virtue of chemistry is that, is it easy? I don't know whether it's easy, but it is always interesting.
Our task, and one of the things that the Dreyfus Foundation has been very good at doing, is to provide the safety for the young people to at least try some of those things. And I think the community has to be enormously grateful to institutions like Dreyfus for making that possible.
The Teacher Scholar Program supports young professors who have proven themselves early in their careers as researchers and teachers. Two very distinguished current board members received Dreyfus Teacher Scholar Awards in the early 1980s. Marianne Fox eventually became the Chancellor of the University of California, San Diego. Matthew Tirrell is now leading the University of Chicago's first engineering school. Many teacher scholars went on to win some of chemistry's highest awards. And today's teacher scholars are equally talented. They are pushing the frontiers of chemistry. The Dreyfus brothers' legacy lives on.
Both brothers felt that chemistry could help improve the world.
The Camille and Henry Dreyfus Foundation focuses entirely on chemistry, so in that way we are distinct.
For the size of the foundation, which is substantial but not enormous, it has a tremendously positive impact on the chemical sciences and on the public appreciation of what chemistry can do for humanity.
Good afternoon to all of you. For those who don't know me, my name is Wanda Andreoni, and I'm Professor Emeritus at the Swiss Federal Institute of Technology in Lausanne. It is my great pleasure to welcome you to the Dreyfus Prize Award ceremony in honor of Professor Michele Parrinello. I feel that in this moment, I represent a vast community of scientists around the world whose scientific endeavors and achievements rest on and have greatly benefited from the groundbreaking foundation Michele has provided. Those who have had the privilege to collaborate with him and the great pleasure to be his friends. We are all particularly happy today that in pursuit of its mission of rewarding breakthroughs in chemical sciences, the Dreyfus Foundation has recognized Michele Parrinello's fundamental contribution to science. His methods have permeated a wide range of disciplines, previously exclusive domain of the respective specialists, extending from theoretical chemistry to condensed matter physics, material science, nanoscience, to geophysics and planetary chemistry. He has thereby given us the tools as well as a unified perspective to tackle a vast world of challenges with unforeseeable depth. All the while, he has time and again led the way with pioneering and far-reaching applications. From the human side of things, Michele's impact has made our scientific interactions more widespread and our scientific life altogether more fun. Thank you, Michele. Thank you for constantly being an enthusiastic and tireless leader. And especially thank you for proving once more the incommensurable value of unfettered curiosity in research, all more vital in this nebulous, transformative era. And now it is my pleasure to give the floor to the Rector of the USI Università della Svizzera Italiana, Professor Boas Erez.
Caro Professor Parrinello, cara signora Parrinello, caro Presidente della Fondazione Camille and Henry Dreyfus, cari membri del Board of Directors della Fondazione, caro Consigliere di Stato, caro rappresentante della città di Lugano, caro Presidente dell'Accademia delle Scienze, caro Presidente dell'Ente Ospedaliero Cantonale, caro Vicepresidente dell'ETH, cara Presidente dell'Università della Svizzera italiana, caro Past President dell'Università della Svizzera italiana, dear Professor Mayer, dear Professor Ward, caro Signor Mantegazza, cari rappresentanti del mondo economico e dell'impresa, cari rappresentanti dei media, cari colleghi, signore e signori. Please allow me to continue in English. What a relief. Huh? Now, so the question I want to address is, what is the difference between a major league institution or a minor league institution, or what is the difference between a major league researcher and a minor league researcher? Now, thinking about this, I was thinking about, maybe because this is an American foundation, I was thinking about a movie, a baseball movie, where I think this limit is well represented. This movie is Bull Durham, which has been considered one of the best sports movie ever produced. In this film, you can see that the difference between major league and minor league is a very thin line. The baseball player played by Kevin Costner in this film at some points says that he has spent the 21 greatest days of his life in the major league, meaning he spent the rest of his life not in the major league, and he spent the rest of his life in the minor league trying to return to the major league. Now, the difference maybe between baseball and science is that usually when you get to the major league, you stay there, but this is not always the case. But certainly Professor Parrinello at some point became a major league player and has stayed a major league researcher. Of course, this doesn't mean that my university, Università della Svizzera Italiana, is a major league university. Still, many important and nice things happen by accident, so it seems. And indeed, it seems like an accident that we were given the opportunity to offer a position to Professor Parrinello. But what I can assure you is that from that moment on, we have paid attention to Professor Parrinello and have tried to offer him the best conditions for him to develop his important research activity. Now, having said this, I would like to stress that despite his stature, as this prize shows, Professor Parrinello has not been very demanding. In fact, quite on the contrary, Professor Parrinello has always appeared to me as a very modest person. Furthermore, as the attendance to today's ceremony shows, I should say once again, Professor Parrinello is also very appreciated for his qualities in his community as a colleague, and one may say for his human qualities. So, learning from him will certainly help us become a major league institution. And for all of these reasons, we're particularly proud and happy that we can share this moment with him and with you today. And so it is my pleasure to call up Henry C. Walter, the president of the Camille and Henry Dreyfus Foundation. Thank you very much.
Turn anything on? Can you hear me? Good, okay. Rector Erez, thank you so much for your warm introduction. I will follow your lead and speak in English. Okay. On behalf of the Dreyfus community and the audience, and we have some board members, staff, and spouses, I want to say how happy we are to be in Lugano. We are grateful to all at USI, and I understand that it's also referred to as USI, is that correct? Who have contributed to this event to honor Professor Parrinello as the winner of the 2017 Dreyfus Prize. Thank you for joining us. The Dreyfus Prize is awarded biennially and recognizes an individual for exceptional research in a selected area of the chemical sciences. It is always special to present the award at the institution of the award winner in the company of their family, friends, and colleagues. This is the first time the prize has been made to a scientist at an institution outside the United States, and we are fortunate indeed that Professor Parrinello has given us this opportunity to come to Lugano. We appreciate it. Thank you. Switzerland is a beautiful country to visit or live in. Personally, I'm always happy to visit because I was born in Switzerland, not far from here, but a few years ago, many years ago. The Dreyfus brothers' formative and highly productive years in Switzerland laid the groundwork for their success. The history of the Dreyfus brothers was outlined in the video shown earlier, and I believe in the program. The Dreyfus Prize honors both the Dreyfus brothers and individuals who have made major contributions in the chemical sciences. I am sure the Dreyfus brothers would be proud of Professor Parrinello's ingenuity and accomplishments, which have transformed so many areas of science. It is a great pleasure to have the honor of presenting him with the 2017 Dreyfus Prize. Professor Parrinello, would you please join me?
How do we go here?
First, I will read the citation. The Dreyfus Prize in the Chemical Sciences is awarded to Michele Parrinello for his groundbreaking developments of molecular dynamics, simulation methodology, and associated landmark studies of chemical, material, and biomolecular systems. Excuse me. Professor Parrinello, on behalf of the Board of Directors of the Camille and Henry Dreyfus Foundation, it is my pleasure to present you with this medal as the winner of the 2017 Dreyfus Prize in the Chemical Sciences.
Here we go. Feeds just about. Thank you.
Guys, you want me to cry? Thank you. Thank you.
Here is a framed version of the citation for you to keep. We'll put it, oh, there's the other bit. Lug it around. And not to be forgotten, this is a check. 250. I can tell you, it really hurts to have to turn this over to somebody else. But here's the check.
Okay,
It's the
thank you.
monetary part of the award, and congratulations.
Thank you.
again.
Thank you. Okay.
So, I think that's it. I'm going back to the podium. Okay. So later. That's it. That's it? Yeah.
È pesante. Sì. Sai che vedi?
I now ask Matthew Tirrell to please come to the podium to introduce and describe some highlights of Professor Parrinello's scientific career. Dr. Tirrell is the Dean and founding Pritzker Director of the Institute for Molecular Engineering at the University of Chicago and a Director of the Dreyfus Foundation. Matt.
Well, it really is a distinct pleasure to introduce Michele Parrinello, the recipient of the 2017 Dreyfus Prize in the Chemical Sciences. Professor Parrinello was born in Messina, Italy, and received his advanced degree in physics from the University of Bologna in 1968. He's held important research leadership positions in universities, national laboratories, and industry, including the University of Messina, the University of Trieste, the Argonne National Laboratory, the IBM Research Laboratories, the Max Planck Society, the ETH in Zurich, and now here at USI in Lugano. In addition to the recognition being bestowed today by the Dreyfus Foundation, Professor Parrinello has been the recipient of numerous distinguished prizes and awards, many of which are cited in the program booklet for this event. He's also been awarded 8 honorary degrees from universities in Italy and abroad, and has been invited long-term visitor to dozens of universities around the world, and including 2 where I was working at the time, Minnesota and Santa Barbara. The main focus of Professor Parrinello's research has been to improve upon the molecular dynamics simulation technology, greatly expand its scope, and apply it in innovative and insightful ways to a variety of important problems. As the power of computers has increased, so has the popularity of atomistic-based simulations increased, and there's no area of chemistry, biology, material science, and many other fields in which simulations are not applied. Right up front, the vast impact of Professor Parrinello could be easily judged from his huge number of citations, somewhere between 60 and 70,000, depending upon the counting agency, and from the fact that hardly any paper that uses atomistic simulations, in particular those based on molecular dynamics, fails to cite one or more of his works, and if they do not, one feels that they should have. Professor Parrinello's contributions have been historical and defining contributions to the chemical sciences. A formative moment in Professor Parrinello's career was his sabbatical at Argonne National Laboratory, lasting almost 2 years, where he was introduced by Rahman to atomistic molecular dynamics simulation. At that time, atomistic molecular dynamics was a discipline confined to a rather small group of scientists that required access to large computers and was rather limited in scope. During his time at Argonne, he developed the so-called Parrinello-Rahman method. This method allowed phase transitions between different crystalline states to be simulated under the condition of constant external stress. In order to appreciate the relevance of this work, one has to go back to the time when it was developed. In those days, atomistic molecular dynamic calculations were performed under conditions of constant volume. Parrinello and Rahman realized that by making the molecular dynamic cell vary in size and shape, entirely new classes of phenomena could be simulated. In a fashion that is typical of the way Professor Parrinello conducts his research, he not only developed the method, but also applied it to systems of interesting practical importance. This particular work is a paradigm of how Professor Parrinello unified computer simulation with rigorous statistical mechanics in order to study key phenomena. Upon Professor Parrinello's return to Trieste, where he had a permanent position, he was concerned about the ability of empirical force fields to describe the properties of materials. His quest for better potentials culminated in the development with Roberto Car, who's here, of ab initio molecular dynamics, or the Car-Parrinello method as it's commonly called. This method combines a density functional theory calculation of the interatomic forces with molecular dynamics in an elegant way. I'd like to note that in the nomination materials reviewed by the Dreyfus Prize jury, the word elegant appeared again and again, along with variations on similar words. At the time, such a feat, this combination of density functional theory and molecular dynamics, appeared impossible, and without exaggeration, its realization in the Car-Parrinello method has revolutionized both the field of electronic structure calculations and of molecular simulation. The impact of this work has been enormous, bringing together communities that were separated, unifying statistical mechanics with quantum mechanics in the simulation field. Once this remarkable breakthrough was achieved, an enormous stream of applications followed, both from Professor Parrinello and from many, many others. One of the first applications was to the melting of silicon, and it was shown that the ab initio molecular dynamics method was able to describe the change in bonding from semiconducting to metallic on melting, a process that's very hard to simulate using standard potentials. Another area of focus was on the properties of water and water solutions, and in particular, the study of the two water ions, H+ and OH-, to give you a glimpse of the diversity of applications. Both of these ab initio molecular dynamics studies were landmarks achieved by this remarkable breakthrough in computer simulation methodology. I believe this quick summary is more than sufficient to give you a flavor of why the Dreyfus Prize jury was overwhelmingly impressed with the accomplishments of Michele Parrinello, and you've heard more than enough about his scientific accomplishments from me. So I would therefore like to invite Professor Parrinello to the podium so that we can hear about his remarkable work in his own words.
Thank you very much. Hello, good afternoon. I'm, of course, overwhelmed. I would like to thank once more the Dreyfus Foundation and the jury that have chosen me for this prize. As it was mentioned, it's the first time the prize goes to Europe, and also it's the first time that it's awarded to theoreticians, I believe. So that's a double hit there that makes me particularly proud. I think we can proceed now with the talk, and that's the title of my talk. And it's not as you think that has to do with my evident Italian accent, but it comes to something that somebody told me. Huh? You can learn to ski as an adult, but it is like speaking a language with an accent. You can do it, but it's never quite right. Hopefully, my chemistry is not as bad as this one is in skiing. To understand why I'm saying this, I'm taking this point of view, I would like to share with you steps in my professional, in my scientific life. So I started studying physics in Messina, and this was the physics auditorium in which lesson, and I remember as a young man passing an exam on the very same desk there with a severe professor in front. And I love this, you see there are these old apparatus, especially to do with electricity, electrostatics, machines that were supposed to produce sparks and never did. And I want also, if you can kind of, can you recognize this chap here? Benito Mussolini. So, because this picture was taken, this very photo was taken from an album on the inauguration day of the university, and so that's why El Duce was there. This physics, but I mean, in spite of the age, I mean, it was identical as when I did the exam. I mean, this must have been in the 30s, and so I'm not that old. So I find it lovely, but you know, everybody has his own strange taste. This is to be contrasted with chemistry. That's how it is. I mean, you can imagine the usual. The usual hodgepodge of different things. And there was, of course, a persistent smell of solvent in this place. And that's when I had my first encounter with chemistry, sorry. But there was immediately a difficulty. My average marks were the top everywhere. In all the subjects, but chemistry. And this was due to this molecule here. It's called the pyruvic acid. And I was asked what the hell, what is a pyruvic acid? And I didn't have the faintest idea. And so I don't. So I went to Wikipedia. And so you can find out for yourself. It's called pyruvic, I understand, because pyros from Greek means you burn, uva is grapes, you burn the grapes, and then out comes this nasty chemical. Here you see how chemists represent a molecule. We come back to that, carbon, oxygen, hydrogen, and this the line represents chemical bonds. Okay, so first encounter was really terrible. Worse could not have been. But I continued, so far away from chemistry, and while preparing this talk, I found a photocopy of my thesis. And I don't know whether you can read it, because I can't read it with my glasses on. So that's the title of my thesis was Rappresentazione relativisticamente invariante di alcuni stati legati, which means in English relativistically invariant representation of bound states. Chemistry has to do with bound state, but this is a far cry from the bound state that we talk about. But so this was a thesis in essentially elementary particle physics. So when I was a student there was kind of a hierarchy of discipline. There were, the real men would do theoretical physics, and in the most abstract of way. Anything practical, or by practical, I didn't mean anything that you can use in the industry. But practical meaning, say, if you do elementary particle, if you try to study this particular reaction, you were already a chemist, which were deemed to be the lowest form of scientist possible. Okay. So, but then things happened. I mean, from bad things, good things can happen. My professor there, which was a very intelligent man, but he suffered from, how you say, some kind of neurosis, and he disappeared for months on end. And so I did my thesis on my own. So that's that taught me self-reliant. And then after giving my thesis, I had top marks in spite of chemistry, and I was expecting, he promised, I'll call you, come in a month and I'll give you a position. I'm still waiting. But from negative things, positive things happens. More or less at the same time, this gentleman here, Mario Tosi, who spent up to that time had spent most of his scientific life in the States, and come back again to the University of Messina, and there you can see where I used to work. And there is, so this is from 1930, but again, it was just a bit worse when I went there. You see, in those days, you see, the Duce was a grand man, so also everything had to be grand, and so the height was enormous. So heating the stuff was very expensive, so the solution was that they divided these big rooms into two. So some of us would stay in the top part, and the other in the bottom part. And I think, I mean, I stayed as a young man, stayed in the top part, and so with the light coming from the bottom, and you see I still wear glasses. Okay. But there was an important change because I started worrying about many body physics, condensed matter, statistical mechanics. So I started going from the paradise to the hell of chemistry. Okay, after a few years, I mean, Messina is a rather old university. I mean, it is probably older than any American university, but I wouldn't say it's quite as famous and vibrant as Harvard or Yale. So I moved to the University of Trieste, and the reason for moving to Trieste was the presence of this International Center for Theoretical Physics, and which is in a beautiful location. I think this must have been the window of my room, and from my room I could look at the Adriatic Sea. Very beautiful location. Never had an office as beautiful, and I shared my office with a person. It's been important, another person important in my life, Elio Tosatti. So this was my office. We were staying here. Then Elio moved to some other office, and eventually I think Roberto Car came here, and in this room we argued about Car-Parrinello. There was a striking difference between Messina and Trieste, especially ICTP. There was a constant flux of famous people, and I have this picture, which I'm very proud, but it's quite accidental how we got it, but you won't tell anybody, because this gentleman here is Paul Dirac, He's a very famous physicist. I mean, it's quite similar to having a picture with Albert Einstein. We're talking a bit of the big of science, the greatest of science. So that, well, I was exposed to millions of new ideas, and my appetite in those days, my appetite for physics was voracious. I would be interested in everything, and still am. And then came the turning point in my life, and I went for a couple of years to Argonne National Laboratory in Chicago. I enjoyed very much the Chicago winters, and Anis is believed to be, and I think by many of us, to be the founder of the molecular dynamics at his practice. Yeah, and I love this photo because it's a representative of how I work together with him all the time, sitting by the side. I was a total disaster at programming, but he was very patient with me, and I mean, he learned me, he taught me essentially all that I know. So now a small digression, because many times I'm asked about what do you do and why you do and so on, and it's always difficult to explain what one does in simple terms, and we certainly, it's not the occasion to go into depth here, but molecular dynamics is a set of numerical techniques that allows the behavior of complex assembly of molecules, such liquid, solid surfaces, and so on, to be simulated. You're familiar fact that the computer can simulate the weather, so you can do the same as with complex molecular systems. And we do this because we like to explain experiment, help experiment, replace possible experiment, predict new phenomena, provide insight, and as we shall see, it's a kind of microscopy, because we see how on the computer how atoms are moving, are behaving, bonds are formed and broken. Okay, so in those days we came up with the in preparing this talk, I realized that my career can be summarized into 4 formulas. And so the first of this formula is this one, the Parrinello-Rahman formula, which we wrote down to enable, you see still my high energy physics background. This is a Lagrangian, a concept which I think not many chemists are familiar with. This is a Lagrangian, and that's was very much influenced by my original background. Using this formula, you can study the transformation of between different solids, and I have here an example of such transformation. But before showing that, I will report here the number of citations per year that this paper is receiving. And the reason why I do that, not because I want to trumpet, I mean, I think if I can be immodest, getting this prize doesn't avoid that I should do that, I mean, preempt it. But you see the pattern. At the beginning it was very, very low, then eventually there's a growth, and now that's an exponential boom. The reason why I say it for the young students and the researchers that are in the audience, that when I started with this work, I mean, people was were a bit condescending. They made very sorry comments. Somebody thought it was all wrong. And this is always the trademark. And if somebody tells you what you do is all wrong, it means you're on the right path. So don't be discouraged. And time, sometimes, is a gentleman. I'll show here an example of this. So this is a crystal of benzene. And we can. No doctoring. That's how they Okay, so the atoms minuet. That was irresistible. So when I saw here these things, I said, okay, we need to put the Boccherini's minuet on top of it. And luckily, one of my collaborators, Giovanni Piccini, managed to do that. And it's quite appropriate, I think. So why do you do it? Because it was said also by previous speaker, chemistry and physics are at the basis of what we do, and there are many problems in the contemporary society which need to be addressed, and science is the only way of going about it. And so the simulations are a pillar of chemistry. Without this simulation, I mean, the progress would be much slower. And there are three areas which I selected in which so people can resonate with, in which the simulation can play a role, and quickly I'll go through three examples. One is drug design, and there are two covers. So there was some excitement years ago because there was a compound, Glivec, that seemed very promising for the cure of cancer, but then the cancer is a nasty beast, and it induces mutations, and then it's no longer things. And even Newsweek realized that it requires understanding and not blind search. This is a movie which was given to me by Francesco Gervasio, who is in the audience. This object represents one protein that if you block it, the cancer cell will not grow. And here is this GVOX, and there is a lot of water. This is an abstract representation of the protein, just to give you an idea of its structure. But there are lots of atoms, it's all very packed thing. And now we have the GVOX, which is our friend who wants to go inside and kill and stop the activity of this protein. And it's a soundtrack of A Space Odyssey. Okay, another area we're talking about environment. We don't want CO2 production. I mean, CO2 is a culprit for global warming. So one idea of getting around the problem is to capture the CO2 and deposit it or transform it into other chemicals which are not dangerous. And you need to capture it, and this, again, a Fanta scientific picture has been provided to me by Wanda and Roger Rousseau, who are here, and they have developed a clever way of capturing oxygen from the atmosphere so as to reduce the global warming. hopefully. That comes from our work. It's a collaboration with the group of Ursula Retterisberger. So we are all familiar with the silicon photovoltaic cell that transform the solar light into electric energy. There's a problem of cost. A very promising candidate for cheaper deployment are perovskite. And the quality, the ability of perovskite to transform into energy, the solar energy, into usable energy, the solar energy, depends on the quality of crystals that are formed. And so we're studying the nucleation of a perovskite. This is in the liquid state. It's all very disordered. These golden things are, it's again an abstract representation of the structure. So start with disorder, and then out of the liquid comes a nice ordered crystallite. Okay. So it's a very important, but I mean, it's a limitation like everything in life. So there are challenges, because we want to study. Life is complicated, more and more complex systems. So more realistically, practically relevant system. We want to study for a long time and with highest accuracy possible. And so then we comes into the picture, and of course, last but not least, in these things, it's always trying to make sense of what you find, which applies to simulation and applies to many other endeavors in human life. So understanding what you do, I keep saying, so what? If people come and say, get a simulation that agree well with the experiment, but you have to ask yourself, so what? What have you really learned with these calculations? Okay. So here comes into the picture Roberto Car, who was sitting in that famous room over there, and where there was, of course, another momentous event in my life, and we feverishly worked for night and day on developing the Car-Parrinello method, which has been said by Mark, that it combines electronic structure and molecular dynamics and brings simulation to a newer level. Of accuracy, possibility enhances the scope. Now, complex chemical simulation can be simulated with a degree of realism which was not earlier possible. And again, we go to the formula number 2. That's it, in its full glory. And I call on Roberto to check whether it's right or wrong. Okay. And it was mentioned because I like it for 2 reasons. I mean, melting of silicon, in my view, was important because you showed that it was possible. And so without any input, just you tell him, this is silicon. So you start with an ordered system. There is no music here, sorry, guys. So, yeah, and at the right temperature, it goes into the liquid phase. But this transition between an ordered to a disordered system is accompanied by massive chemical transformation. So chemists are used for good reason of thinking of chemical processes as a succession of single events. So you break one bond, then you go something, form a new compound, then do something else, you do something else. Here, everything happens together. It's all together. There's no, so here one goes from local, what I call local chemistry, which has its role, its power, to non-local chemistry, where a whole fraction, big fraction of the system is involved. And this, without this null locality, the transformation would not have occurred. Okay, so after that, we became very famous, started getting prizes here. I forgot, we have, I should have put it there, a picture of Roberto and myself in black tie, looking like to satisfy penguins for some prize. So we were famous, we started getting offers, in particular was attractive for me. An offer was made at the suggestion of this gentleman, whom you know, Heinrich Rohrer. He's a great man who was the inventor of the scanning tunneling microscope together with Gerbini, and he got the Nobel Prize for that, but he was also a person of great foresight. And he immediately after the discovery of the tunneling microscope, he started talking about the nanosciences, which is something that has grown enormously. But also he started talking, he realized that this development needed the accompaniment of simulation. And that's why he hired me, where I started. So this, again, it's a nice spot. And started a group there. And there are some our presenter, Andreoni. You can recognize here Ursula Rettlisberger. And I cannot go through Francois Gigi. So there are not very famous scientists. And unfortunately, I couldn't find a picture where we are all together. And so I have to supply another picture here, where this is still me, a few kilos less. And this young lady with this mane over here is, who recognizes her? Julia. Okay? And she's in the audience, so together with Gigi. And actually, this group was fatal for this encounter. Now probably Julia would be there, and I would be here learning from her. Okay, so but that was a great time. I must say it was. I don't want to use vainly the word family, but we really lived together day and night. There was no Saturday, no Sunday. It was a great time. And there are other people that were with me, that come later, because things at IBM were not as stable as they used to be in the past. And so I got an offer from the Max Planck Institute in Stuttgart, and there I met yet another important person in my life, Ole Krogh Andersen, who is in the audience. And this looks really bleak, but it's not like that. That's the Max Planck Institute in Stuttgart. It's much better than this, but it was supposed to be, so this picture was given to me by Carmen Rovira, who is from Barcelona. Unfortunately, she had a problem, she couldn't come. She sent this picture and said, this was my friend. So you imagine a Spanish lady from Barcelona, first day of work, she was confronted with this landscape. Okay, so here you can't really see. Can we dim the light, please? Because okay, that's slightly better. But here there's Jurguta, Professor Marx, Carme. I can't even hear, I have to look there. Carla Molteni was here. So again, a bunch of very very now famous people that helped things. And scientifically speaking, this time the kind of together was a continuation of one kind of research into the other, a continuous evolution. And from that time, a different moment, a different code came about. CPMD, who is now developed and looked after by the people in Zurich at IBM, and CP2K that started while Jürg Hutter was there in my group, and now is becoming, is really the responsible for this thing, and is getting more and more popular. They're both based, of course, on the paper, in one form or another, on the paper that we did with Roberto. Wanda was a big thing, and then alias and Ali. So Ali was not in my group at the time, but I want to show a movie anyhow to make a point. So we have to, this is water, oxygen into hydrogen. These are, okay? And there are two waters which are different. One water which has one extra proton, so it's positive. And then there is a water with less, with one less proton, which is negative. Of course, these two guys want to combine, and they do in the most fantastic and complex way. That's my blaster of methanol, and has this fluid kind of behavior. So this gets rid of the proton goes through these things over there. So fantastic things. Why do I say fantastic? Because the way old-fashioned chemists were used to think about reaction was a bit like this scheme. So you have a molecule, you have another molecule, you bring them together, you have to pass the energetic barrier, and you go into the product. Where is this energetic barrier? Is there, can you define it? It's all very complicated. So and again, it's a non-local chemistry, because the event that brings the proton to move from one water to the other involves so many actors that they cannot really be described as a particular conformation of atoms in space. So again, it's a non-local chemical thing. And in fact, I say this with great respect. One thing that I learned in my being more and more involved in chemical projects is the fact that the chemists, theoretical chemists, are a very clever lot. And they know many things, and should never be underestimated. Of course, many people are aware of these limitations. And it also must be said that the standard approach has had so many successes that it's difficult to abandon. But it seems to me that many times some of the chemical research, they look like the Procrustean bed. So you wonder who is this Procruste and what this bed has to do with research. So Procuste is, we are now in ancient Greece. So Wanda will be happy. And Mr. Procuste was a bandit who sat in a mountain pass between Athens and one of the major temples, where you went to know your future. And of course, at the end of the mountain pass, wayfarers were tired. And Procuste offered the bed, and of course the pilgrims were very happy to accept it, but there was a catch. So the guy would put you on a bed. If your legs were longer than the bed, he would sew it, If it were short, I would pull it so as to fit it. So many papers are like trying to fit something more complicated to a scheme which doesn't really apply. Okay. We are getting close, going in the year 2000 now. We get from 1930 to 2000, but that's not so bad. So by this time I stayed many, many years abroad, and it's been a great experience. Met many people. I mean, I felt nostalgia, felt a bit homesick, more than of Italy, of the Italian culture, Italian language, and so on. And I had a great opportunity of coming here without having to abandon the support, the quality, the organization that I got used to over the years. And so I moved here first. Spent the first years of my time at CSCS under the auspices, of course, of ETH, and eventually I moved as main job at the Università della Svizzera italiana. And of course, I have to be thankful to many people here for allowing me the leadership of ETH, the leadership of USI, first Marco Baggiolini, and later in a big way, and also Piero Martinoli, and of course now the new one, Boas, Professor Erez has been very kind to me so far, and that's. Okay, here. You know, human life, I mean, that's a factor. I mean, if you get to over 70 like me, and you don't learn that nothing is forever, I mean, you lost these 70 years. Okay, so that's one of the first group that I had here, and there's an important character, unfortunately not here, but Alessandro Laio. Also, well, it's too bad the quality is, Giovanni Bussi, and so on, and Francesco Gervasio. Alessandro is not here, but that was the time when we came up with the new formula. So, but before talking about the formula, I tell you again what the driving things are, which led to the formula, the drive consideration. So to move into these two other axes, one complexity and one time. Why do we want to study complex systems? I have a beautiful example by Giulia Galli here. So you know that there's a problem with the energy. Solar energy is a possibility, but you get solar energy only where there is the sun. When at night, you don't get any solar energy. So possibility to store, an area in which one would like to move is to be able to store the energy and use it at a later stage. One possibility is to produce hydrogen. So if you take two water molecules, you can form two hydrogen and oxygen. Hydrogen is a fuel, so you can burn it. Rockets are powered by hydrogen. So you, during the day, you produce bottles after bottles of H2, and then when you need, you warm your house, and so on. And if you burn hydrogen, you produce only water, so no nasty chemicals. Also, I mean, yeah. But look at this, how you produce. Huh? So this has been given to me by Julia. This is where the light comes. It's a complex structure with different, there's a soft material, hard materials, there's water, there is defects in these materials, there are solute in water, temperature, and so on. So everything comes together, and the whole system works because they all come together. You can't simply separate one thing from the other. It is the system that works. And it's very, very difficult to I had this talk by Julia not long ago, and I really like the choice of the problem, also what she has done. That's a really shows how far we have gone and how far we have still to go, and how many new uncharted territories we have to tread. Okay, the other. Okay, so you say, oh, but why do you worry about these things? I mean, you have your simulation. You can do ab initio. You can put your system together, let it run like experimentalists do, and see what happens. But there is a major technical problem, which is that these simulations are costly, so you can't and take time, and the cutoff time for research is, say, 3 years, because the time PhD students takes to produce his thesis. And if you take in consideration all these facts, also the technological limits, you see that we cannot go very far in simulation. So you start your system, the system evolves, and this evolution corresponds in real time to 1 picosecond, 1 nanosecond, and so on and so forth. And so that shows how far we can go. So if you use CSCS, we can go study system up until, I would say, under 1 nanosecond, millisecond. You can get it cheaper by using GPU things. Now you can be a millionaire. That's a remarkable story. This is the show who made money at Wall Street, and then he decided to invest like 60 million of his money into building a new computer, his own computer. So he has a particular hobby, and if I compare the hobby of the show with the hobbies of, say, Berlusconi, I think they invested the same amount of money overall. But the output is not of the same quality. Okay, sorry, but otherwise we go to bed. So essentially, the limit of technology, bottom line, that's I better the limit of technology is about 1 millisecond. And there are a number of phenomena which are beyond that. One is nucleation, which I said, or the drug binding, and so on. So we need to push our ability to simulate matter in this region of time, for this length of time. Now, I will not go into the details, but I mean, because too technical for but it's a bit like when you move in a very rough landscape with many valleys, and to go from one valley to another. This is Switzerland, as in the Swiss Alps, and to move it's really painful, because you have to climb mountain passes, after mountain passes, and so on. So the going is rather difficult. Okay, so when you have some basic difficulties, you go to classics for inspiration. And what could be more classic than the Bible? And so, let's say, you go into Isaiah, every valley shall be raised, every mountain shall be made low, the rough ground shall become level, the rugged place a plain. So let's set our research program. So take Switzerland and transform it into Devon. So from rough mountain to smooth hills, so where it's easy to move. But then, of course, you never forget that you really want to explore there. So you should be able to go from Switzerland to Devon and from Devon to Switzerland. That's called reweighting. Okay, and so this is performed by our third formula, which describes what we call beta dynamics, and I'm sure you will immediately see why. But I mean, behind the formula, there's a very simple protocol, which can look here. If I don't do anything, I remain trapped here. And if instead give a help, so to fill the valleys, the going becomes much easier. And there is an old way, which we developed with Alessandro Laio, and a more modern and more sound way, which we developed later with Alessandro Barducci and Giovanni Bussi. And I cannot help, almost at the end, showing this. It's the same plot as seen by a Dutch person, Bert Ensig. So you know that in Holland there are 20 ways of saying rain, and that's it. So there's our unfortunate walkers. He wants to go out, takes hours to go here, hours to go there, but then a helpful cloud comes, feels, and it starts to float. It moves over there. It's a bit shocked, but keep going, and then. Okay, there's here, and there we go. Okay. Okay, so, but that implies, so we go back to our GVEC problem. This can be turned into real science. For instance, we can calculate the unbinding time for this very important drug, 74 milliseconds, which is far above what we could do with brute force and money, like by simply using theory to help us solve problems. Okay, so this has evolved into something which we have developed with Omar, which I saw him in the audience. And that's yet another formula. And that's my present group. A bit enhanced by visitors here, some of them very young. And I've always been blessed with many great people, both scientifically, humanly. And I write a formula of the future. The best formula is yet to be written, not yet, almost there. I would like to thank all the people that over the years have made my life so very special. Thanks to the Dreyfus Foundation, of course, and thank you for your kind attention. I believe there is closing. I mean, we go for food now, no? What is the program, boss?
Before that, I wanted just to wish to thank you for this very inspiring talk, and I also would like to thank all those who have made this afternoon so very pleasant. So, of course, all the speakers, but especially the organizers, and all of you who have joined us, and also traveling from USA, from India, from all over Europe, and probably from north to south, the UK, Ireland, and Denmark, Germany, France, Italy, Spain, and Portugal, and of course all the various cantons in Switzerland.
I think there is a special person I would like to thank you. She put a lot of effort and energy. It's Daniela Wills, who deserves a big hand.